Hello everyone, my name is Pravin Mariappan and I'll be giving you a video presentation about coagulation dryer system for pan polymerization plant as per requirement of mechanical system design for the semester. Along with me is NANTHAR, AMEERUL, SURESH and Michael, and our supervisor is APIR Dr. Hamdan. Next, let's take a look at the presentation outline. Now, let me give you a little introduction to the project. So our group 21 is tasked to design a polyacrylonitrile pan coagulation drying and packaging plant. And the main task for our project is to produce 100 kg of pan powder per batch. So our process starts with the aqueous pan slurry that's obtained from group 8. Our group is to produce PNID, PFD and also all relevant drawings as well as plant plan layout based on literature review and appropriate methodology. Next, let's take a closer look at pan. Polyacrylonitrile or pan is characterized as having high mechanical strength as well as thermal and chemical resistance. It is a versatile polymer that's used for a big variety of products. The main selling point for pan fibers is that it is the chemical precursor of high quality carbon fiber, which makes it very expensive. Now, let's take a look at the problem statement for this project. The main challenge for this project is the limited information on process data for coagulation and drying process that is available online. Next is the high viscosity of the coagulated pan slurry. Pan slurry is said to have a glue-like consistency which makes it very hard to be transferred. Next, pan polymer oxidizes in the presence of air easily, so the equipment needs to be flushed with inert gases such as nitrogen to prevent oxidization. Coagulation must be also maintained at a steady temperature of 5 degrees Celsius to ensure optimum coagulation. The main objective for this semester is to design a plant which has the capacity to produce 100 kg of pan powder per batch. After that, we need to design equipment with regards to the relevant governing equation and come up with detailed drawing of two major equipments. Finally, we need to ensure the project is feasible and can be completed within the set time period based on project scheduling.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AMEERUL HAZIQ and today I'm going to talk about our group PFD drawing. So this is our group PFD drawing. The feed will enter the reactor, then the coagulation process takes place after chemical reaction. Chill water will be used to cool the reactor by running it through the jacket and will be supplied by the cooling tower H001. After that, pump P003 will be used to pump the slurry mixture to the dryer unit, which consists of flat belt conveyor and hot air blower. In the dryer unit, the pan polymer will dry until powder are formed. Then it will be sent to the roll miller M001 to grind the solidified mixture to fine powder or up to desired mesh. Then the powder is processed into pouches and sealed by the packaging machine. Now I'm going to talk about our group PNID drawing. So this is our group PNID drawing. Compressed air will be pumped through pump P001 and nitrogen tank T002 will supply nitrogen gas. Both of the compressed air and the nitrogen gas will enter the vessel R001 and also the rotary dryer E002 for dilution purging process to ensure inert environment for both equipment. So during the process, air will be vent out from both equipment through this line. Then feed will enter the vessel R01 through this line. The feed will then cool rapidly by chill water immersion coagulation. The chill water is supplied by water tank T001 containing 85% of water and 15% of ethylene glycol. The mixture is then pumped to the electric chiller E001 before it goes into the vessel. Since the pan is insoluble in water, it makes it easier to be separated using filtration technique since there is nothing in our vessel. The wastewater will be drained through this line into the sump tank T003. Then the coagulated mass is then discharged into the screw injector P004. Then the screw injector will extrude the coagulated mass into the rotary dryer E002. Once the coagulated mass is fully extruded and the pan layer is set across the length of the dryer, the electric oven is switched on until the pan polymer is completely dry.
Okay, I'm Nanda and I'll be talking about the detailed drawing of the high pressure coagulator today, which is the equipment ID R001. So this is the detailed drawing of the high pressure coagulator. So it's too small now, I can't zoom, but later I'll show the important parts. Okay, so this is the isometric drawing, and this is the isometric drawing of the high pressure calculator with all the components attached to it, and these are the individual components of the high pressure calculator. This is the nozzle list, this is the design data, this is the bill of material, this is general notes, and yeah, so let's in closer. So this is the detailed drawing. This is the detailed drawing of the equipment with all the components attached to it. So this is the isometric drawing. We can see all the components, basically the steel structure, the top head, the body, the lower head, the support lugs over here. Yeah, so stuff like that. So this is the top view, the front view, and the side view. We have this is the lower head and the body, the lower head and the body. So the main important thing here is the body has three openings for a glass cover, so that we can see the level of the fluid inside the high pressure coagulator, and this is the steel structure. So have this is the top head. The top head also has two viewing pins. This is the two viewing pins for us to see what's inside the hydrocalculator. This is where the stirrer goes. This is the manhole, and this is the nozzle for the valve. This is the mechanical seal, and this is support lug details. And here's the nozzle details. And this is the stirrer details. We have two propellers and one gear. And lastly, we also have this wire mesh.
I will explain about the detailed drawing of our rotary dryer. This will be our rotary dryer. Our rotary dryer has the capacity to evaporate 233 kg of water from 333 kg of wet cake in 1 hour operation. So this will be our detailed drawing, which is being done using AutoCAD. So this one will be our raw metal feed, which also can be called as feed chute. The feed pipe slope is greater than the natural inclination of the material, so the material can inflow the rotary dryer smoothly. This will be our exhaust outlet, where it removes off gas and small particulates. Alright, this will be our rolling system, which comprises of riding ring and trunnion wheels. The riding ring is a part of the support structure for the drum and provides a place for pressure to be absorbed, where the trunnion wheels serve as the cradle for the rotating drum, helping to ensure smooth and concentric rotation. So this will be our drive assembly, which comprises of motor, gearbox, and gear and pinion. Our gear ratio will be 1 to 5. This will be our discharge head, where product exceeds the dryer. This section is where the drying air is directed through the drum from combustion chamber. This will be our air seal, which connects the discharge head to the rotating drum in order to keep air and material from prematurely exiting the drum. This will be our drying shell. Our drying shell is made from carbon steel SA285 grade C, and there is total of 20 flights which act as a material lifter, maximize heat transfer between the material and the drying air. So the all dimension present in this dryer is being calculated using heat transfer equation, which is being enclosed in our report. So thank you.
Let's look at the plant layout. This is the isometric drawing of the top view, the front view, and side view. The 3D plant tool. Let's look in detail into each equipment that we have. So the first equipment we have over here is this is the this is the nitrogen gas generator. So this nitrogen gas generator is a huge machine by itself, which generates the nitrogen gas, and also has a booster system, which so we don't need a compressor. So it then pumps nitrogen gas into this piping, which sends it to the pressure vessel. Then this over here is the air compressor, which compresses air and sends it to the pressure vessel as well. Okay, now let's look at the water system. Okay, one sec. Okay, so what we have here is the water system. So this is the water tank. From the water tank, water enters the chiller, electrical chiller. From the chiller, the water is cooled down to desired temperature, negative temperature, and then the water is then pumped back into the pressure vessel over here, as we can see. Okay, and then from this blue pipe is to represents water pipe, and then we can see here that this is the sump tank. Over here is sump tank. So water from the drain nozzle enters this pipe, this brown color pipe enters this pump. The dirty water is then sent to the sump tank. So the sump tank is then cleared accordingly. So now let's look at the pressure vessel. We can see the motor at the top of the pressure vessel, and then at the bottom we can also see, wait, let's look in detail at the bottom, zoom in a bit. Okay, alright, nice. So at the bottom we have this is the screw injector. So this is the drain nozzle, it enters this brown pipe. So this screw injector, then the remaining fluid inside here, when all the water has been drained, it enters this screw injector, and then the fluid is then pumped into this blue color piping and into the rotary heat dryer. Okay, now let's look at the rotary heat dryer. Okay, so then we go to the rotary heat dryer, 3D view. Okay, so with the rotary heat dryer we have this is the feed inlet, and this inlet is from just now the nitrogen gas. The nitrogen gas acts as a purge gas, and then this is the vent gas, and when the powder has been dried, it then enters here, it then comes out here, and it goes along this track as it by the help of this conveyor. Okay, now let's look at the conveyor, zoom in. Okay, now it enters this conveyor, and from this conveyor it then enters this ball mill. It uses conveyor, go up, and it enters this ball mill. Then inside the ball mill it is grinded into fine mesh size, and then it exits the ball mill, comes out through here, and then from here it enters the packaging machine. This is a packaging machine where it is packed into desired mesh, desired pouch, maybe 5 kg pouch, 10 kg pouch, and then these machines are used to bring the pouches to storage. So that's all from me
Hi
today.
everyone, my name is Michael Davis. I will be explaining the plant costing and also the plant scheduling. So first, we have the total procurement of raw materials and equipments. Our main equipment, the coagulator and the rotary dryer, is highlighted here. So the total procurement for the equipments is 1,278,000. So for the total plant installation cost is for our site and our warehouse fabrication. The total would be 10,271,000. Alright, from the two plant installation costs and the procurement costs, we can calculate an estimate of capex to be 15,681,000. And for our OPEX, we calculate the monthly expenditure of 3,249,000. Take in effect for plant maintenance and vehicle servicing. So from there, we expect our annual OPEX to be around 8,250,000. So from there, we can calculate our revenue from production. We can expect an annual revenue of 60 million. We expect to see our money return starting from the 5th year, and we expect to reach $500 million after 15 years of production. Next, the plant scheduling. We estimate a total of 410 days to the first plant production sales. To simplify, the tasks are segregated into different teams, procurement such as tendering, contracts, awards, and then we also have the designing for our PNID design. Governing equations also inside PNID design, and construction, installation for all the equipments, and also we have the testing, inspection and testing team, and last but not least, the sales and
Summarize our
production.
project. Our aim is to design a coagulation and dry unit for PAN polymer manufacturing plant which has the capacity to produce 100 kg PAN powder per batch, and the objective has been achieved. Plant costing comprises for capex, opex and revenues taken seriously when designing the plant. Our project has been confirmed as feasible as the IRR is higher than the MERR of 10%. Our group expects this project will proceed to the fabrication and testing of the plant, which then focus the effectiveness of the plant by improving the efficiency, which can bring a good return to the Malaysian economy. That's all from our group. Thank you.